In this section, we're going to be working with algebraic operations of functions and also with composite functions. So to get started, let's go ahead and look at algebraic operations of functions first. Now, when we talk about algebraic operations of functions, it's just as you'd suspect when you're adding, subtracting, multiplying, and dividing, but there are a few things that you need to look for. So first of all, let's go ahead and look at the rules, and then when we're talking about the rules, we'll also talk about domain restrictions. So the first restriction that we need to keep in mind when we're working with functions is the denominator can never equal 0. So remember, we have a numerator is our top number of our fraction, and the denominator is the bottom number. And it has to be true that the denominator, whatever it is, whether it's x or x plus 2, it cannot equal 0, ever. The denominator cannot equal 0. You cannot divide by 0. If you try this on your calculator, you'll usually get a syntax error or something similar. The other restriction that we're going to be looking at is we're going to be talking about the square root. So if we're simplifying an expression and we end up with the square root of a negative number, that's not possible in the real number system. So I cannot take the square root of a negative number. Okay, this is not possible in the real number system. So these are the two things that we're going to keep track of when we're talking about algebraic operations of functions. So let's go ahead and look at our simplified rules now. So to get started, functional notation we know is something like f of x and g of x. But what if we had something like, in parentheses, f plus g of x? Well, what that means is just take function f and add function g. So this just means f of x plus g of x. Now the same thing will work with subtraction, as you might suspect. So if I have function f minus function g, I just subtract the two functions, f of x minus g of x. Same thing works with multiplication, fg of x. Remember, when your variables written together, it means to multiply. This just means f of x times g of x. And now we also have division. Now with division, this is the one that we need to be careful of. So for instance, we might have f of g, f divided by g of x. This is just equal to f of x divided by g of x. But now we have this restriction. G of x cannot equal 0. And we always have to remember that when it comes into play for determining the domain of a particular function. So whatever the denominator is, the denominator cannot be equal to 0. So what we're going to do now is we're going to look at some basic functions and then talk about the domain of each function. Now remember, the domain can be anything except these two things up here, where the denominator equals 0 or where the square root is with a negative number. So that's what we're trying to keep up with here. So let's go ahead and find the domain. Now usually if an expression doesn't have a denominator or a radical, our answer is any real number. So let's go ahead and look at a polynomial expression. Let's look at 6x plus 3. So the domain of 6x plus 3 is all real numbers. Now the reason it's all real numbers is that there are no denominators to restrict, and there's no square root signs to make sure that what's underneath the square root sign is non-negative. So all real numbers is my solution here for the domain, and I would represent that from negative infinity to positive infinity. And of course, this is interval notation, and with interval notation, wherever we have infinity, I have to use parentheses, never brackets. Okay, let's look at another example. This one has a denominator, so that means that's where I need to be careful. So for this one, f of x equals, let's say, 4 over x minus 2. Well, there's no square root signs here. There's just this denominator. And the rule is the denominator, x minus 2, cannot equal 0. So I take that denominator, I say it cannot equal 0, and then we solve this just like we would any other equation. So here, these would cancel, and I get x cannot equal 2. Now there's no shortcut way of writing this in my math lab, and we like to have our answer in interval notation. So if we say it cannot equal 2, if we were to graph this on a number line, here's 2. So it's saying I could be everything to the right and I could be everything to the left, I just can't be 2. So I'm leaving this gap here at 2. So this would mean negative infinity to 2. I have to use parentheses at infinity, of course. And I also use parentheses at 2 because I cannot equal 2. And then I use a union symbol, and then I start up again right after 2. That's how I show this with parentheses and go off toward infinity. So this is my solution in interval notation. So it's all the numbers to the left and then all the numbers to the right. That's kind of what we're looking at. So there's an example with a polynomial expression, and then I also see one with a denominator. So if you have a denominator, all you do is you take the denominator, say cannot equal 0, and solve. Let's go ahead and look at this on a calculator as well. So if we were to look at the function 4 over x minus 2 and graph it, we'd hit y equal, and then we'd have 4 divided by, like we do over here, but we have to make sure we have a parentheses around the entire denominator, x minus 2. And let's go ahead and hit graph. And then we can see in our graph, this graph is continuous here, and remember domain are my x values. It's continuous here, but there's this gap right here, and it looks like it's around 0, 1, 2, 3, around in here. So if I look over here on my table, if I go second table and look at these values, I can see I have a problem here at 2. That's where it says error. So that's why this is showing me again that x cannot equal 2, because I have an error there. Now, our calculators we have to be careful of, because when they graph, they're really only playing dot to dot. They don't know any better, so sometimes they connect points that shouldn't be connected, and in this case they didn't. But what we have on this particular graph would be called a vertical asymptote. So basically right here at x equal 2, there's this dotted line, and the graph does not cross that point. Okay, so this is an asymptotic line, and you can see that to the right the graph gets closer and closer but never crosses, and then from the left it does as well. So we can also see for my x values negative infinity to 2, and then it jumps, and then it starts up again right after 2 and goes toward infinity again. So sometimes graphing these can be helpful as well. Okay, let's go ahead and look at another example. Sometimes you could have more than one denominator, and again we're trying to find our domain here. Let's go ahead and look at the function h of x equals 1 over x minus 4 over x plus 2. Well, right now I can see there's no square root sign, so let's go ahead and go with the denominators. This one says x cannot equal 0, and this one says x plus 2 cannot equal 0. So these are my domain restrictions. This one on the left is already solved for. Over here on the right I would subtract 2 from both sides, and I'd get x cannot equal negative 2. So if I wrote these on a number line, of course we'd go in order from negative 2 being the smallest to 0. I can have all the numbers to the right of 0, between negative 2 and 0, and to the left of negative 2. So that's kind of what this looks like. So let's go negative infinity to negative 2. That would be this portion. This portion would be negative 2 to 0, but again I'm not including those points because at negative 2 and at 0 it's undefined. Union, and then I start up again right after 0, so I have a parentheses here and I head off toward infinity. So this is the correct domain for this. Now let's go ahead and graph this as well. So I have 1 over x, so I have 1 divided by x, and then what was the rest? Minus 4 over x plus 2. Now when we divide by x plus 2, you need to make sure this is in parentheses. The entire denominator needs to be in parentheses. And let's go ahead and hit graph. We can see as this is graphing, something's going on right here, and then something's going on right here. It's kind of getting closer and closer but never quite touching. So that's kind of giving me an indication of my domain. And remember, domain means our x values. So let's go ahead and pull this into our notes. And then we'll also look at the table as well to help us decide what points these are. Now all of these points have been integers so far. If we ran into a problem where they weren't integer values, we'd have to, of course, do a little bit extra work because they're not going to show up on the table or be easy to find on our calculators. But it's a good idea to kind of visualize these and see what, see what the values are saying and what the graph looks like. Okay, so something's definitely going on here because I have that error and here I have that error, so at -2, so -1, -2, that's that vertical asymptote, and then at 0, so if you notice this is going up, this one's coming down, and it's never crossing. So I can definitely see that something's going on, the function's not defined at those points. So again, the domain are all my x values, -infinity to -2, and then I can go from -2 to 0, points not included, and then start right after 0 and head off toward infinity. Now we've looked at a polynomial function, a couple fractions. Let's go ahead and also look at a radical function. Now with a radical function, when you want to find the domain, basically you're looking for a restriction. Okay, so we're looking for a restriction where the radical cannot be negative. So let's go ahead and have a look. Let's make one up. So let's find the domain of f of x equals the square root of x minus 3. So we look at the radicand, which is everything under the radical, and we say, okay, that x minus 3 cannot be negative. So let me write that differently. X minus 3 has to be greater than or equal to 0 in order for this to be true. So then, because this has to be 0 or larger, greater than or equal to 0, we could add 3 to both sides. And I see canceling, and I have x is greater than or equal to 3. So if I plug a 3 in here, 3 minus 3 is 0, square root of 0 is 0, that works. I could plug in a 4, 4 minus 3 is 1, square root of 1 is 1. But I can't plug in a number, let's say like -5. -5 minus 3 is -8, and I can't take the square root of a negative number in the real number system. Now if we were to graph this on a number line, x greater than or equal to 3, we can see that this would be, okay, and then we have this value of 3, so here would be 3. Now greater than or equal to, this would be a bracket, and greater than or equal to is to the right. So for interval notation, my domain would be the interval from bracket 3 to infinity. Now I can equal 3 because I can take the square root of 0, and it's not in the denominator, so I'm good there. Let's go ahead and look at one other example. Actually, let's go ahead and graph this one too. F of x equals square root of x minus 3. So here we have square root, whoops, let's clear that out of there, square root x minus 3. Now again, domain is our horizontal values. So if we look at this graph, we can see something clearly is going on here starting at 3. Now if we look at our table over here, we can also see that I have all these errors, and then starting at 3, my function starts to be defined. So again, that's indicating that my domain is from 3 to infinity as well, because x values are my domain. Okay, let's go ahead and look at an example in a denominator where we have a radical. So we're still trying to find domain. And here we're trying to find the domain, let's say, of h of x equals, let's say, 2 over the square root of 3x plus 1. Okay, so now we have a little bit of a different problem. We have a denominator and we have a radical. So I take this radicand, 3x plus 1. Now last time I said greater than or equal to 0 because it was in the numerator, but now I'm just going to have to say greater than 0 because it's in the denominator. So it's in the denominator, so I have to say it's greater than 0. It cannot be equal to 0 because it's in the denominator. So I'd subtract 1 from both sides, divide both sides through by 3, and I get x is greater than -1/3. So here's -1/3. Now greater than is a hollow point or a parenthesis, not a bracket or a filled point. Greater than moves toward the right. So my solution for the domain and interval notation would be parenthesis -1/3 off toward infinity, parenthesis of course. So let's go ahead and graph this one. It's not going to be really easy to see what's going on here. So 2 over square root of 3x plus 1. So y equal, let's clear that out, 2 divided by square root, and under the square root we have 3x plus 1. So we're going to get an idea of what this looks like, but it's going to be hard to determine the domain from this. Okay. So when we look, we can definitely see it's going off toward positive infinity, so that part seems to be good. But what's hard to tell is what's happening in here. Now if we look over here, it looks like our domain should start at 0, but we also have to remember that this is not taking into account any integer, or only integers, not any decimals. So the domain kind of helps us see what's going on here, that something's going on over here just a little bit. And we could use the trace function to see what's going on here as well. But basically it's not an integer value, so it's not going to be easy to find. Now trace button is over here to the left of the graph button, and if you notice as I'm tracing, I'm moving this to the left, I kind of jump off the graph all of a sudden. So I get clear over here to this negative 0.22, and then it jumps off the graph, and it's that it can't be that accurate. It can't go by hundredths and thousands. It has to go by these certain decimal values. But it's telling me I'm getting pretty close to about negative 1/3. So graphing doesn't help a huge amount here, but it kind of does verify what's going on in terms of it looks like it's about right. So that's working with algebraic operations of functions. Now this is kind of a new topic. This is going to be looking at not inverse functions, but compositions of functions. Now composition of functions basically means you're plugging one function into another. Now this is very different than the problems we just did, so you have to be careful to pay attention and not confuse the two. So composition of function has a special notation, and it looks like this. F and then this hollow point. It doesn't mean multiplication, it means F composition G. It doesn't mean multiply, it means composition. And it means plug one function into the other. And we'll talk a little bit more about this when we get to some exact examples, but this means F composition G of X. Same thing, different notation that you'll see. And some people call it FOG because it looks like F of G, and that's how we pronounce it, F of G of X. Now, what we want to do then is we want to talk about what this actually equals when we are working through this type of problem. It means in my function F, I plug in the entire function of G. So it means F of G of X, and that's how we read it. Now this is a little bit harder to work with until we get some actual functions put in here, but I want to just put down a couple other rules. F composite G does not equal G composite F as a rule. I can't depend on basically the commutative property to work here. I can't say F of G equals G of F in these particular cases. Now, this means to plug one into the other. It does not mean to multiply. So F of G does not equal F times G. So this hollow point here, I need to be careful when I write it. This is a hollow. F of G does not equal F times G. So again, it's important to note those. And these are really good questions for, the lecture quiz that you'll probably have over this. Now, what does composite function mean? Well, let's go ahead and look at some examples. Let's say that F of X equals, let's say, 2 over X, and G of X equals X plus 4. Let's go ahead and look at composite functions. F of G of X then, and I like to write these with different notation than this. I like to write it F and then in parentheses or brackets G of X. This means in my function F, I plug in the entire function G. So G in this case is X plus 4. And that came from right here. So this means in my entire function F, wherever I see an X, I plug in X plus 4. So F of G of X is 2 over X plus 4 for this case. Now G of F of X just means the opposite. It means in my function G, plug in my entire function of F. Okay, well F is equal to 2 over X. And my function G is X plus 4, so in place of X, we'll put a 2 over X plus 4. Now notice this x only goes under the 2, not the 4. So I have this rewritten, and you can see that these are not equal because this 4 is not in the denominator, it's its own term. So you have to be really careful here about when you're plugging these in. Now a lot of times in my math lab homework, you won't be given the original functions, you'll be given the composite function and then asked to figure out where it came from. So let's go ahead and look at one of those examples as well. Oh, and before we do that, we probably better talk about the domain here real quick too. So the domain for this problem, we can see pretty clearly here that x cannot equal 0, so we'd have to be very, very careful of that. And then we can also see from this piece that x cannot equal negative 4. So for this problem, at the very top, the f of g of x, we'll start a new line here, so domain for f of g of x is, okay, so for our domain here, we can see we'd want to go for x plus 4 cannot equal 0, and we'd subtract 4 from both sides. So x cannot equal negative 4. And of course in interval notation this is negative infinity to negative 4 union negative 4 to infinity. So there would be my domain for that particular value. Now another thing that we can say is we can say negative 4 must be excluded. So that's another way to talk about the same thing. So sometimes when you're working these problems, they'll say what should be excluded, and we'd say negative 4 should be excluded, or if they ask for the interval notation, you would use this one. Let's go ahead and look at the domain for g of f of x. Okay, so that was the 2 over x plus 4. Well, if we look at this one, the only problem is our denominator here is that x cannot equal 0, so I'd have to say 0 should be excluded from the domain. So you have to keep track of your domain just like we always do when we're working with these types of functions. I'm going to go ahead and pull in a problem from my math lab so you can kind of see some of the wording that you might run into. So for this first problem, they tell me what f of g of x looks like. Over here they're saying my function f is basically 3 over x minus 7, and I need to plug in this entire function g. G is 14 over x. Okay, so let's try that. So this would be 3, and then g of x is equal to 14 over x minus 7. So this is f of g of x. Okay, then it says 0 and what number should be excluded. Well, the 0 is the easy part right here because this comes from the fact that x cannot equal 0 because of this denominator. Now if we keep simplifying this, however, I need to find a common denominator here. So I have 14 over x minus, this is 7 over 1, but if I want to find a common denominator, I'd multiply top and bottom by x. So this would look like 3 over 14 minus 7x all over x. Okay, now this is getting a little bit confusing. X still cannot equal 0. But we have to remember our rules. When you divide by a fraction, you multiply by the reciprocal. The reciprocal means to flip it, so the x would pop up top, and then the 14 minus 7x would be in the bottom. Now I can't change my rule on my restriction of my domain because this was in the domain. X cannot equal 0. So now I take this piece, 14 minus 7x, and I say that cannot equal 0. So subtract 14 from both sides, divide both sides through by negative 7, and I can see x cannot equal 2. So there's another restriction. So I have x cannot equal 0, and that's from here, and then I have x cannot equal 2 after I go through and I simplify this layered fraction into the denominator. So my second value here, it says if f of g of x is equal to this function, then 0 and x, actually we don't even need to put in the x equal here, so in our box, then 0 and 2 must be excluded from the domain. So that's the type of problems that you'll see running into this in your My Math lab. Okay, let's go ahead and look at some other easier ones. Let's look at x squared minus 14x plus 3. There's no square roots, there's no fractions with a denominator, So my domain would be all real numbers then. Now all real numbers in interval notation is negative to positive infinity. And of course we never bracket infinity. Negative to positive infinity is my domain then. Now what if I had a polynomial like this in the denominator? What if we had f of x equal, let's just make up one, let's go 24 over x squared minus 26x plus 165. Some big numbers there. Now the problem would be, where does x squared minus 26x plus 165 equals 0? That's going to make this undefined. So my domain would be taking this denominator and saying that denominator cannot equal 0. Well, the first thing we want to do is think about factoring this. Now, whichever method you use, AC method, you could also use reverse FOIL. I always like to graph these because that gives me an idea. So x squared minus 26x plus 165, and my numerator was 24. So let's hit y equal, clear this out. So we'd go 24 divided by x squared, what was it, plus minus 26x plus 165. And let's graph this and see what happens. Now we might have to expand our screen a little bit here. Might not be able to see much going on. And we really can't see too much. We can see that something's going on right here. There seems to be a split in the graph. I'm going to go a little bit further over here in the x direction. So I'm going to extend out my window in the x max direction. Let's go ahead and go out to, let's say, 25. So we can see from this graph that something's definitely going on right in here somewhere, and right over here as well. And if we go to second table, we should be able to figure out if they're integer values where they cross. Now, those were clear over maybe like toward 10 or 15, so let's scroll a little bit. Oh, it was at 11. So I can see at 11 I have a problem, and I have another problem at 15. So my errors basically are telling me where my intercepts are. So 11 and 15. So let's go ahead and pop that back in here. So that means this factors into x minus 11, x minus 15. Now we say these cannot equal 0. Now if you were to FOIL this out, we'd have minus 11x minus 15x is minus 26x. 11 times 15 is 165. So then I'd say x minus 11 cannot equal 0, or x minus 15 cannot equal 0. So I'd add 11 to both sides. So I'd say x cannot equal 11. Add 15 to both sides. X cannot equal 15. So in this particular problem, I'd have to say the values of 11 and 15 should be excluded. Or if they were asking for interval notation, I would say negative infinity to 11, union 11 to 15, union 15 to infinity. Now if you have a tough time coming up with this interval notation, just do a quick graph. So I have 11 and 15, and basically I can be any number except these. So I'd have hollow points there, and I'd interpret each part of this then as this interval, negative infinity to 11, 11 to 15, and then 15 to infinity. So these can be a little bit tricky, but a combination of knowing the rules and graphing can go a long way to helping. Okay, so let's get back to the details about composite functions. So for an example, we could run through two given functions, let's say f of x and g of x. Let's look at f of x equals 5x minus 3, and let's look at g of x equals 5x squared minus 4. And let's look at some composite functions. So for our first, f of g of x. Okay, remember that means f of g of x. This means everywhere I see an f in my function, I will plug, or x in my function, I'll plug an entire value of g is, which is 5x squared minus 4. So f is 5x minus 3. So this is 5 and then x minus 3. But what is x equal to? Again, x is equal to the entire function g, 5x squared minus 4. And then I would simplify by distributing through the 5. So that's 25x squared minus 20 minus 3. And of course we can combine like terms. So I have 25x squared minus 23. So when we're working with these, we can also talk about the domain. So this one, I don't see any domain restrictions at all. All real numbers. Negative to positive infinity, there's no denominator, there's no radical. So this is an example of f of g of x. Let's look at let's do g of f of x now. So same two functions. Let's look at g of f of x. That means everywhere in my function g, I'm going to plug in the entire function f of x. Okay, f of x in this particular case was 5x minus 3. In my function g was 5x squared minus 4, so 5x squared minus 4. Now the reason I left this blank was we have to plug in the entire function f into this blank, so it would be 5x minus 3. And of course we can't just leave it like this. We would want to FOIL this out. I can't distribute the 5 through here. I have to leave the 5 out front. And that's going to be 5x minus 3 times 5x minus 3 minus 4. So 5x times 5x is 25x squared. Outsides would be minus 15x. Insides would be a minus 15x. And last would be a plus 9. And then the minus 4 is on the outside. So we could simplify 25x squared minus 30x plus 9, and then minus 4. Distributing through the 5, I have 5 times 25 is 125x squared minus 150x plus 45 minus 4. And then of course those last two are constants, so we can combine those as well. So this is g of f of x. Now we could talk about the domain here as well. So for the domain, there's no denominator and there's no radicals, so my domain is all real numbers. Now we've looked at f of g of x and g of f of x. We can also look at evaluating these. So we're still using our same two functions, so let's write those down again since they're off the screen. We had f of x equals 5x minus 3, and we had g of x equals 5x squared minus 4. Okay, so now let's look at these in terms of evaluating functions. Let's look at f of g of 1. Okay, so this means I will plug 1 into g and get an answer, and then I'll take that answer and plug it into f. So f of g of 1. So I start and I plug the 1 into the closest value to it. So g of 1 in this particular case is going to be 5 times 1 squared minus 4. Now 1 squared is 1. 5 times 1 is 5. 5 minus 4 is 1. So this boils down to f of 1. So that means I plug 1 into my f function then, which would be 5 times 1 minus 3. Now it just so happened that the 1 plugged into g also produced a 1 that I'd plug into f. That doesn't always happen. So when we simplify, I have 5 times 1 is 5, 5 minus 3 is 2. So f of g of 1 is equal to 2. I could also do this for g of f of 1. So let's do the same thing for g of f of 1. So that means everywhere in my function of g, I'm going to plug in an f of 1. So I take the 1 and plug it into the f and get an answer, and take that answer and plug it into g. Well, f of 1 is going to be 5 times 1 minus 3. 5 times 1 is 5. 5 minus 3 is 2. So I get 2 when I plug 1 into f. Then I take that value of 2 and I plug it into g. So g of 2 then is equal to 5 times 2 squared minus 4. So 2 squared, I have to do the exponent first. I can't multiply first. 2 squared is 4. So I have 5 times 4 minus 4. 20 minus 4 equals 16. So actually plugging in numbers here works as well. Now some of these problems, after you find the composite, you might end up with a denominator or a radical. And remember, with a denominator or radical, you have to be careful to restrict your domain so that the denominator cannot equal 0, and also that the square root has to be 0 or larger than 0 if the radical happens to be in the denominator. Again, sometimes in my math lab you'll be given a composite function that's completed already, then asked to come up with the pieces. And what you want to do with those types of problems is you just kind of want to go through and analyze what's going on with the function and try and determine what two functions could I have combined to get, the function that's given. There's one other type of problem that you'll run into in my math lab that sometimes is a little bit confusing, causes a few questions. So let's go ahead and look at that one last example. So for this example, they say, what is g of f of 1? Now we can see here that the blue is my f and the g is my red. You can tell from right here. Well, remember what composite functions mean. This means take a 1 and plug it into the f function. Well, here's my f function. If I plug in a 1, it looks like to me that I get a 7 back out. So let's have a look. G of f of 1 is equal to g of f of 1. And I like to put brackets to distinguish what I'm plugging in. And I just found out that when I plug 1 into my function f, I get a 7 back out. So f of 1 equals 7. And the way I got this is I read the graph, and I'm looking at my f function, so the blue graph. If I plug in a 1, I get a 7 back out. So now this says, in my function g, I want to plug in that answer of a 7. So I come over here, and I plug in a 7, and I read clear down to here, and it looks like I get negative 9 back out. So g of 7 is equal to negative 9. So this just means you just need to plug in 1. You plug into the f first, get your answer, take that answer and plug it into the g. Good luck on this section. Remember, domain restrictions have to do with where the denominator equals 0 and where the radical is undefined. And you have to be careful when the radical is in the denominator, because even then the denominator cannot be 0 as well. So be careful, keep track of domains. If you have any questions, please make sure you bring them to class. You can stop by my math lab, or the math center in the library, or stop by my office. Good luck.